Hi everyone, and welcome to a new video about noise analysis of op-amp circuits, and this is our example number 6. In this example we'll look at the different circuit, which is very similar to the example number 5, but in this case we have the filter in series with our input signal. So we have the inverting amplifier again, but this time it is not the feedback capacitor, but it is a series capacitor which is in series with the input resistance. Now we will of course look at the calculations and also the simulations in SPI, so that will be also worked out step by step. So let's look at our example. What we have is the following circuit. We have R1 as 1 kilo ohms in series with the capacitor, which has three values: 1, 10, 100 nanofarad. So we will discuss each case. And the feedback resistor is 5 kilo ohms. And we have the op-amp OPA 209. What we want is the calculation of the input referred RMS noise voltage and the output referred RMS noise voltage. So the solutions, we always start with the op-amp specifications, in particular with our noise specifications. So we will use the OPA 209 datasheet. You can find these plots in the datasheet of OPA 209. You can see on the left side the input noise voltage spectral density, and on the right side you see the input noise current spectral density. In addition, we have some parameters and defined at some test condition, like the open loop gain, also the frequency response of the op-amp in this example. Now the first parameter we will discuss and use is the DC open loop voltage gain, which is given by this symbol. It's here, and it is 132 dBs. It's also given here in the table. In addition, which is a very important parameter, is the gain bandwidth product. It is 18 megahertz, and that is actually shown here in the frequency response part. Now that is for the gain bandwidth product. Now we have several specifications considering the noise performance of this op-amp. We have the broadband noise voltage spectral density, which is given by this symbol. It is 2.20 nanovolts per root hertz, and that is shown here in the table, and the units are shown here on the right side. And it is defined at 1 kilohertz and 2 higher frequencies. This is also seen in the plot here on the left side. So if you look at this and you make the you determine actually the values of this line, horizontal line, this part of the graph is independent of the frequency. This part is dependent of the frequency, and is also called a 1 over F noise part, and it's called the broadband or a white noise part. Now in a similar form we have the broadband noise current spectral density, which is given by this symbol. It's then 500 femtoamps per root hertz. That is shown here in the table, and that is also defined at frequency of 1 kilohertz, but this is also determined from the graph for the input noise spectral density, noise current spectral density. You can see this is 0.5 pico amps per root hertz, which is exactly equal to 500 pico femtoamps per root hertz. Now also we have here a region which is frequency dependent, and this is a region which is frequency independent. So we have the broadband and also the 1 over F noise current part. Now let's look at these two regions also, the 1 over F noise voltage spectral density, and it is defined at 0.1 hertz. It is given by this symbol. It has a value of 20 nanovolts per root hertz, and that is actually shown here. At 0.1 hertz, it is 20 nanovolts per root hertz. You can of course also take the value of this input noise voltage spectral density at 1 hertz or maybe another one, but you need to of course stay in this region, which is then the frequency dependent part. Now in a similar form you can look at the 1 over F noise current spectral density, again defined at the same frequency of 0.1 hertz. By this symbol it is 3.75 pico amps per root hertz, and that is shown here again at 0.1 hertz. We have a value of 3.75. Now we have now the necessary data to move on with the next step in our example. So let's look at the circuit performance. Now that we have for this circuit the gain, and in particular we have the signal gain and also the noise gain. The signal gain is actually the gain where this circuit behaves as such that it has its maximum value. Now that is the case when the capacitor here is a short, and if the capacitor is an open, or if the capacitor behaves in a different way, you will have of course a lower signal gain. So the maximum gain I can get here is given by this formula, which is then the familiar formula for our inverting amplifier. It is not a DC gain, it is not a high frequency gain, it is actually a gain at some specific frequency, and this is also called the mid-band gain, because this circuit will behave, as we see shortly, as a bandpass filter. But we also have the noise gain, which is a very important parameter, and that is defined as a source which is connected to the non-inverting input of the op-amp, and then the noise at the output due to this noise voltage source at the non-inverting input of this operational amplifier. Now for that analysis, we set the input signal source to 0, so we actually disable it, and we make sure that we have the maximum possible gain. And now for that we again short this. That will be of course for specific frequency, and then this will be gone, and we have done 1 kilo ohms here and also 5 kilo ohms and the feedback. Now for that, looking from this non-inverting input, we will see again the non-inverting amplifier formula, which is the 1 plus the R2 over R1, and it will result again in a noise gain of 6. So we have the signal gain and the noise gain. Again, we see that the signal gain is different than the noise gain, because we need to use a noise gain. This is just given as a discussion that the signal gain can be different, and in most cases it will be different, but it must be not used in our noise analysis. So the bandwidth, we have also two specific bandwidth. So we have the closed loop signal bandwidth and we have the closed loop noise bandwidth. Of course we are interested in the noise bandwidth, but before we move on, let's also look at the signal bandwidth. If you consider the circuit this without the capacitor, so actually the capacitor is short, then this circuit will be dominated, or the dynamics of the system or the circuit will be dominated by the pole of the op-amp only. And that can be determined, or the cutoff frequency or the signal bandwidth can be determined by the gain band product over the noise gain. Now we have 18 megahertz from the datasheet over 6, which is then what we have for this circuit. It will be 3 megahertz. And this is what we call the cutoff frequency. And if you consider this, of course, as a bandpass filter, this will be then the upper cutoff frequency. Now we have an op-amp which is in series, just one op-amp in series with a RC high-pass filter. You might ask, why is it a high-pass filter? If you have a DC, for example, DC operation here, this capacitor will be an open. That means it won't allow the current flowing from the left to the right side. So it is not passing the DCs. If you make the frequency higher, for example 1 terahertz or even larger, this capacitor will approach to a unity or a short. That means actually it is a high pass filter because it passes the high frequencies. Okay, that means we have actually one part which is the frequency dependent part here in this series part, and we have also the dynamics of the op-amp, which will be of course determined by the noise gain and also the gain bandwidth product. So the pole frequency P1 associated with this high pass filter R1 and C is then given by this expression. Again, very familiar formula. Now let's also look at the condition for several cases for the capacitor. First, 1 nanofarads, that will result actually in this expression, and it will give us 159.2 kilohertz. If I increase the capacitor to 10 nanofarads, my pole frequency will be 10 times smaller, will be 15.92 kilohertz. If I go to 100 nanofarads, the pole frequency associated with this RC circuit, R1 and C, will then be even 10 times smaller, will be 1.592 kilohertz. So you can see the pole frequency will decrease by a factor of 10 by each increase of the capacitor by a factor of 10. Now, we know that this circuit has two frequency dependent parts, which is just the R1 and the C, that will determine the frequency, and also the op-amp itself. The R1 and C behave as a RC high pass filter, which is this part. The op-amp with the noise gain will behave as a low pass filter, so if you only consider this with the resistors R1 and R2, that will be a low pass filter. So the high pass filter characteristics here and the low pass filter characteristics is shown here. You can see the P1 will determine your cutoff frequency for the high pass, and the P2, which is then actually this pole, will determine your cutoff frequency of the low pass filter. So just looking at this two plot, it is in separate form a high pass filter and low pass filter. Now, since this will be of course in cascade, so you will then have a effective band pass filter by cascading a high pass filter and low pass filter. So you will have actually a plot like this, where you see the P1 and P2 again at the same location, if of course P1 and P2 are pretty much far away. If it is too close to each other, then this value will shrink and you will also have some other cutoff frequencies. So the pole frequency P1 is a high pass filter pole, and the pole frequency P2, which is then the signal bandwidth here, 3 MHz, is a low pass filter pole. And that is then due to the op-amp's gain bandwidth product and noise gain due to the resistors. Now, the closed loop signal bandwidth is determined by the pole frequency P2. Why? Because the signal bandwidth is 3 MHz, and this value here is very small actually. This one is pretty small compared to the 3 MHz, and this one is also not that much, and it's approximately 0.16 MHz. So 0.16 MHz is again not a very large number compared to the 3 MHz. So you can see this is considered to that one a very small value, and it is for sure certainly case for these two cases for the capacitors. So you can see that the signal bandwidth will be approximately 3 MHz, and then we can say for the first approximation we can assume that the circuit will behave as a first order circuit. Now we know the brick wall conversion factor. In order to of course calculate and analyze the circuit in noise performance, we need to make a conversion or use a conversion factor which goes from a signal bandwidth to the noise bandwidth. So the noise bandwidth, the closed loop noise bandwidth, is then this scaling or the conversion factor times the signal bandwidth. Now we know that the conversion factor for the first order system is pi over 2. Multiplying this by the 3 MHz will give you the noise bandwidth. So let's do that. It is the noise bandwidth, it is then this value, and if you now substitute the values for the Kn and also the signal bandwidth, you will have 4.71 MHz. So you can see this is again much larger than the signal bandwidth, but we need to use this noise gain and a noise bandwidth in our calculations for noise. Okay, now let's continue with the total noise. It's of course determined by the input referred RMS noise voltage, which we want to determine, and also the output referred RMS noise voltage will be then the result of this input referred RMS noise voltage. Now the relation between these two is given by this expression, which is then very familiar expression where you see noise gain again in picture, because the output referred RMS noise voltage is the noise gain times the input referred RMS noise voltage. So the input referred RMS noise voltage on its own is then of course composed of 3 parts, because the input has some noise due to resistors. It has also some noise due to the model of the op-amp source. So we have the current source and the voltage source, which is then defined by this op-amp. So you will have a contribution of the noise voltage source and a noise current source, and also the terminal resistances of these two resistors. So that will be also again the terminal noise voltage. Now, the input referred RMS noise voltage is then composed of 3 parts. Again, the input referred RMS noise voltage than due to only the internal op-amp noise voltage. That is given by this symbol. So this will have the noise at the input referred only due to this one, and it will be given by this symbol. Now, in a similar way, you have the input referred RMS noise voltage due to the internal op-amp noise current, which is then given by this. So it will also cause some input referred RMS noise voltage. And then finally, we have the input referred RMS noise voltage due to the resistors. That is then, of course, calculated using the thermal noise voltage formula. Now, the input referred RMS noise voltage is calculated using the root sum of squares. And for that, we take these three values and square them, add them up, and take the square root. That will be the effective input referred RMS noise voltage. Okay, now let's look at the first one, which is the input referred RMS noise voltage due to internal op-amp noise voltage source, which is actually this. So how much noise do we have at the input due to this only? Now the value that we are interested in is on its own also composed of two parts. This is the 1/f noise and also the broadband noise voltage. So that is also a situation we need to consider. We also want to, of course, use these two elements, and that is then combined together to have an effective value for the input referred RMS noise voltage due to the internal op-amp noise voltage sources. Now this is this symbol, and it's calculated using, again, root sum of squares. And then if you have this expression, you will get directly your input referred RMS noise voltage due to the op-amp noise voltage source. Now the broadband noise voltage, we know that it is in RMS, so we have the following expression, which is then given in RMS, will be the spectral density, noise density, times the square root of that noise bandwidth. Now, looking at the datasheet, we also have the 1/f noise part, and that is then determined or calculated using this formula. The FH here is the noise bandwidth. The FL is at some specific frequency. It's most of the time taken as 0.1 Hz, and this is a parameter we need to calculate in the next steps. So FH, again, the closed loop noise bandwidth, so it is then here 4.71 megahertz. This is a selected value, so any other value will do in that region, which is frequency dependent, or the 1/f noise part. And that is here, that's 0.1 Hertz, because it is most of the time commonly taken as 0.1 Hertz. Okay, that's now the broadband and also the 1/f noise parts. Let's move on and look first to the normalized noise voltage. Normalized noise voltage is actually the following. You only consider this one, E sub F norm, and that is then given by this formula, because it is then E at F, so that's actually what we have here, 20 nanovolts per root hertz at specific frequency. And if you now take the square root of that frequency, you will get 6.325 nanovolts RMS. Now we now know what we can do with this number, because that's just a substitution in this expression, and then you can work out the square root. Now we know the capacitor value will generate, of course, some noise bandwidth, but it is, since it is on the left side of the body diagram, we won't see much of an effect of that. So we have then a noise bandwidth, which is then given by 4.71 megahertz, but it is for each case of the capacitor exact same, because this capacitor will create with that resistor R1 a high pass filter pole. So the low pass filter pole, which is of course an upper cutoff frequency, is determined by the signal gain and the noise signal bandwidth, I mean the gain bandwidth product, and also the noise gain, and that is then determined from there using the conversion factor, and it will be 4.71 megahertz. Now, if you, of course, calculate this using the EBB here, 2.20 nanovolts per root hertz, and then the square root of this noise bandwidth, you will get 4.78 microvolts RMS. Now, for the similar part, which is then 10 nanofarads, you will have exact same noise bandwidth, because it has not affecting the upper cutoff frequency of our system. Now that will also, again, the broadband noise voltage, the exact same, and also for 100 nanofarads. Now, if I now also work out the 1 over f noise voltage part, which is then given by this expression, just substitute these values in here, use the noise bandwidth formula here and divide it by 0.1, take the ln, and then square root that value, you will have these expressions. Now, we need to, of course, calculate the input referred RMS noise voltage due to only the input noise voltage source of the op-amp. And that's this. You can actually see it is 4.78 microvolts RMS, because this is dominating the situation here, because it is 4.78 microvolts RMS and this is just 26.6 nanovolts. So this is definitely much larger than that one. Then we have this value here. Okay, that's done for this, and we again see that it is the dominating part is the broadband noise voltage. The next one is the input referred RMS noise voltage due to the internal op-amp noise current source, which is this one. So how much noise will be calculated using this and also the rest of the circuit. Now for the calculation, we will use the equivalent resistance, because the source will see actually this R2 and also the R1, considering that this is a perfect short for specific gain. And the noise current source of the op-amp is then given by IN, and that will be of course then calculated in RMS. Now the equivalent resistance seen by the node, or the current source of the op-amp. So that is the resistance which must be seen by the current source of the op-amp. So it is actually for this current source that we determine the R2 and R1 will be a parallel. Now then we have of course that using Ohm's law we can say this is just what we had as the input noise current source in RMS, and this is the equivalent resistance determined by the R1 and R2, since at specific frequency the capacitor will be a short. Now the IN, which is the noise current source of the op-amp in RMS, it's on its own also composed of two parts, because we have also seen that it is a 1 over f noise part and also the broadband part. So that will then result in the effective value of the noise current source in RMS of the op-amp, which is then calculated using the root sum of squares. And that was then the formula. Now, if I now first look at the broadband noise current, which is again a very similar formula, use the input noise current spectral density times the square root of that noise bandwidth. Now we will determine the values for each capacitor case shortly and summarize that in a table. Now we have also the 1 over f noise current, which is then given by this expression, very familiar, also similar to that 1 over f noise voltage. Now if I first calculate this normalized current, then we can move on and determine the noise current source in RMS for each capacitor cases. Now the FH here is the closed loop noise bandwidth. FL is some specific selected frequency for that 1 over f noise current, and the value of that FL is commonly taken as 0.1 Hertz, but any other value will do if you just stay in that 1 over f noise region. Now let's first calculate the normalized noise current, which is then this, and that is given by this expression. So the normalized noise current is equal to that symbol, which is then actually the value at that 0.1 Hertz. So it's actually this one, times the square root of the value which we have used to determine the 1 over f noise current densities. So we have the 1.186 pico amps RMS that will be used here in this calculations. Now for the capacitor, again we have the 1, 10 and 100 nanofarads, and the noise bandwidth are shown here. Now the broadband noise current, which is actually here, that is in this case 1.09 nanoamps per root nanoamps RMS. How can we calculate this? It is calculated using this formula. You look at your op-amp specification, you will see it is 500 femtoamps per root hertz. That will be then multiplied by this one, will be then shortly used in this expression to have the effective value for our noise current source of the op-amp in RMS. So this is then calculated for the broadband noise current, and for the 1/f noise current we will use this formula, again using this normalized noise current value, and these are the results. We can see it is all the same. It's 4.99, approximately 5 picoamps RMS. Why is this same, and why is also this the same? Because noise bandwidth is a constant value, so it is not changing here for each capacitor. Okay, then if I now use these two, that will be then the input RMS noise current, which we then can determine using this expression, so using root sum of squares. Again, the dominating part here is the broadband noise current. Now, if I want to calculate that equivalent resistance, because this is just given in the amperes and I want to move to volts, so let's then use the equivalent resistance in this circuit, and that is then the parallel combination looking from the source, current source, noise current source. It is a parallel combination of R1 and R2 using this formula. Again, I have 833 ohms. Now, using Ohm's law, since we know this for each capacitor case, then I can say it is given by this expression. So the input referred RMS noise voltage due to the internal op-amp noise current, here this is the symbol, is equal to this symbol times the equivalent resistance. Now you know this, it is 1.09 nanoamps RMS. I just multiplied it by the REQ and I will have my input referred RMS noise voltage due to the internal op-amp noise current source. So then we have the following. So we have approximately 905 nanovolts RMS, and it will be the same for each capacitor. Okay, that's then for the second part of this analysis for my input referred RMS noise voltage in total. Now, the input referred RMS noise voltage due to the resistors, that is calculated using the white noise or the thermal noise formula for the resistors. Now, the equivalent resistance is actually seen at the input nodes of the op-amp. So it is at this node and also at this node. Now, since we of course are interested in the resistors as the equivalent resistance, actually we can say if I now disable this, that means actually open, and also disable this one and also disable this, that will be a short, that will be a short, that will be an open. Then I can see at this node I see R1 in parallel with R2, and at this node I just see ground, so that won't count, so you will only have your equivalent resistance of R1 in parallel with R2. Now, the thermal RMS noise voltage for the resistors is given in general by this very familiar formula. So again, the square root of 4 kTr noise bandwidth. Now, these are the results. We have the K, which is the constant of Boltzmann's constant. It has a value of 1.38 times 10 to the power minus 23 joules per Kelvin. The temperature is given by T. It is, in this case, also in kelvins. And let's say in room temperature, which is a little bit hot area, you will have a round value for your capital letter T, which is 300 kelvins. Now the R is here the equivalent resistance in ohms. So this is just a general formula, but now you can say this is R equivalent. The noise bandwidth is the value in hertz, so you need to actually insert here the value in hertz. For this circuit we have, of course, the R is equal to R equivalent, which is 833 ohms. Now again, getting back to the capacitor and also the noise bandwidth table, this is again very important. Now if I now go to the thermal noise voltage for each capacitor cases, the capacitor won't change the noise bandwidth. So the noise bandwidth will stay the same, so I can always substitute in here 4.71 megahertz, and this will also not change, so you will actually have a constant value for your thermal noise voltage for this specific case. Now the total input referred RMS noise voltage, now this one will be calculated using these tables. It is then calculated using the root sum of squares. Now this is the actual expression, square of this one plus the square of that one plus the square of this one, and then add them up and then take the square root. That is actually how he should find this. So what we have is then the input referred RMS noise voltage determined by 3 elements. Okay, now we also of course can calculate we have also calculated the input RMS noise voltage due to that input noise current of the op-amp. This is again here given as a reference, and we have the input referred RMS noise voltage due to that RMS noise current source of our op-amp. Okay, now combine these using this formula, using the root sum of squares, you will have these values. Again, it is all the same, approximately 9.4 microvolts RMS. In this case, this is actually the most dominant part, but this is also dominating, actually contributing significantly. This is the not really significant part in this example, which is then the input RMS noise voltage due to this noise current source of the op-amp. Now, getting back to the subject also of the output referred RMS noise voltage, that can be determined using the noise gain of the circuit, which is then 6. So that's then formula using the noise gain and also the input referred RMS noise voltage. For each case I have then this expression or these values, which is then 56.4 microvolts RMS, and that will be the same for these 3 cases for the capacitor, because noise bandwidth won't change, so we will just have this value times 6, and also for these 2 cases. So we have now determined actually the necessary values for the input referred RMS noise voltage and also the total output referred RMS noise voltage. So let's also look at the very important parameter, which is the signal to noise ratio, and then check the results in simulations. So the signal to noise ratio, SNR, is a measure that compares the desired signal level to the noise level. Now, in a more precise form, the definition is actually the ratio of a signal power to the noise power. So it is not the voltage, but it's actually a ratio of the powers. And it is often expressed in decibels or dBs for short. Now, you can have a ratio which is higher than 1, that means you have more signal than noise, but you can also have a ratio which is between 0 and 1, that means you have less signal than noise, or you have more noise than signal. Now in dBs, if you have a value which is larger than 1, that means actually larger than 0 dBs, and if it is between 0 and 1, that means you have a lower signal than noise, that means you have a negative value in dBs. So the SNR in this case for this circuit at the output for a specific frequency, we will see later on at what frequency that will be, can be calculated using this expression. So we have then 20 log of 1 over that output referred RMS noise voltage. You can see already that it is given in dBs using that 20 log. So this is the value we had for each case of the capacitor, so it won't change, so this is all the same for all cases. Now if I now substitute this in here, I have now 85, very close to 85 dB. Now if we now summarize the result for each capacitor, we have the noise bandwidth for each capacitor, again all of them are the same, and we have the input referred RMS noise voltage, the output referred RMS noise voltage, and we will see that this will be of course the same for all capacitors, and we have then 85 dBs in SNR. Okay, that is now the result what we have for our signal noise ratio. Now let's then look at the simulation results. First, the frequency response, which will be then given, which will give us the signal gain and also the bandwidth. So this is the frequency response. Again, you can see, looking at the blue line, for example, it is a bandpass filter. So you have the lower cutoff frequency. This is then for the capacitor of 100 nanofarads. This is the lower cutoff frequency, which is then 1.592 kilohertz. And you can see here is actually the same for the blue, the green, and also the dark red line. This upper cutoff frequency is almost 3 megahertz, which was the signal bandwidth for this circuit. Now you can see this is the green line, which is then for the capacitor of 1/10 nanovarads, and the dark red line is for 1 nanofarads for the capacitors. So we can also see this gain, which is called the mid-band gain, is approximately 14 dB. Now this is a little bit closer than 13.98 dB. If you use this value in this formula to move from the dBs to scalar, that will be a 5, and that is actually what we also had as a value for our signal gain. Now these are the parameters, and the summary is actually the following. The mid-band gain for each capacitor will be approximately 14, and that will be also in a simulation 14, so that is a confirmation. Now the upper cutoff frequency, which was in our case 3 megahertz, that was our signal bandwidth, but it's also the same for each capacitor. In this case it is 2.98 megahertz, which is very close to 3 megahertz, so that is actually a very nice result. The lower cutoff frequency for 1 nanofarads is 159 kilohertz. That's for 1 nanofarad, and I can see it is here 150 kilohertz approximately. And why is this smaller? Because the interaction between these two frequencies, or the pole frequency here on the left side and the pole frequency on the right side, is closer, or actually more dominant present than these two poles. That's actually because they are a little bit closer than these two poles. That's why we have actually a reduction in the simulation for the lower cutoff frequency. Now for the lower cutoff frequency of 10 nanofarads, it's actually here, and it's actually very far away from this pole at the upper cutoff frequency. You can see it is 15.9 kilohertz calculated, but it's also simulated, so they're actually the same. Now the cutoff frequency, lower cutoff frequency for 100 nanofarads, it is 1.59 approximately kilohertz, and it is actually also the same in the simulation. So in this case, the only error we get is due to that 1 nanofarad, which is very close to that second pole due to the op-amp and also the noise gain. Okay, now the next one is the input noise voltage spectral density. You can see for each capacitor value that we have a dark red line, which is then for the capacitor of 1 nanofarads. This is then for 10 nanofarads, and the blue line is for 100 nanofarads. Now, if the capacitor value is increasing, you will have actually more filtering. That means actually you have less input reverted RMS noise voltage. But if you look at, for example, this one, the dark red line, you can see again the 1/f noise part and also the broadband part. But since again this capacitor will filter out the noise, all of these cases will approach asymptotically 0 volts per root hertz at the input. So in summary, we have a frequency dependent part, which is 1/f noise, and we have also a frequency independent part, actually this part. And larger capacitor produces a larger input noise voltage density, so that what we also see here is that the frequency is independent part, so it's the 1/f noise part. Again, the frequency independent part, which is in the broadband noise region. But the important thing is here that the larger capacitor produces smaller input noise voltage density at DC approximately. So since the larger capacitor will also filter out more, that will produce less noise. So this is the largest one, the blue one, and you will have 10 and 1 nanofarad. So if it is small, then you will have actually less effective filtering. Now the input noise voltage spectral density will also approach 0 as the frequency approaches infinite values. So that's actually the conclusion for the input noise voltage spectral density. Now looking at the output noise voltage spectral density, we see the following plot. Again, the 1/f noise part and also this broadband region. What is really interesting is it's actually also coming up and then again falls down and approaches very close to a 0 value. So why is this first peaking and then goes down? That's actually due to that high pass filter action, because it will go down for a very low frequencies and then approach that broadband region. And then this capacitor in combination with this R1 will be dominating actually the noise at some frequency. But then this pole of the op-amp and the R1 and R2 will be then also comes into play, and that will again now try to bend this and then make this noise go to zero. And that's actually why we have this plot. Otherwise, if this were not placed here, this will again approach to very high values, because the high pass means actually it will pass high frequencies. So again, it is frequency independent part, which is this part, frequency independent part, and the output goes to zero due to the band limiting of the op-amp in this case. Now the total RMS noise voltage, which is then the output, you can see for specific capacitors, C1 nano, 10 nano, 100 nanofarads, it all approaches the same value of 56.1 microvolts RMS. We had calculated 56.4 microvolt RMS, so that's a really nice result, and all of them approach the same value no matter which capacitor you take. Now, signal to noise ratio is also very important. Let's also look at that one. You can see it started very large at DC approximately and then goes down, and you cannot discriminate actually these plots from the capacitors, but then it will here have some difference, but then they will again come together and approach actually a value which is very close to 85 dBs. Now we have of course also calculated that for each capacitor value it is also 85 dBs, and the simulation gives us 85.02 dBs, of course very close to what we have calculated. So this is also a very nice result, and it confirms also that this simulation result is confirming our calculations for this circuit. So we have now seen actually for this circuit several parameters. We have calculated that step by step and also seen this in the simulation results, and there's a really nice result that the capacitor in this case is not dominating the output noise current. It is actually dominated by this and the noise voltage, of course, at the output. It is dominated by the op-amp and also the noise gain due to that R1 and R2 of this circuit. So that was for this example number 6 about an inverting amplifier having a series RC high-pass filter. This is also called the differentiator, but it is of course has a higher upper cutoff frequency. So in total, if you look at the plot again and the body plot, it is a bandpass filter. So it is a filter which is called a bandpass filter. Alright, that is for this example. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time.